Okay, this is Mr. Moon, and today we're going to be talking about significance tests for mu1 minus mu2. So we're looking at now tests of significance for the difference between two means. We've done a lot of stuff similar to this. Before we've done difference between two proportions. We've also done a confidence interval for the difference in two means, but today we're actually doing the significance test. So we're going to be looking for a t-statistic comparing to alpha equals 0.05 and seeing whether we have a significant result or not. So as you know before, and actually this is a paragraph that I've copy-pasted from a previous slide because it's that similar. When we have an observed difference between two sample means, that can reflect an actual difference in the parameters, or it could be just due to chance variation in random sampling. Like we might get a sample of really tall people from one school and really short people from the other. Significance tests help us decide which explanation makes more sense. Obviously, if a result is super unlikely, like less than 5%, we generally will reject the null hypothesis and say that the parameters are actually different. So the null hypothesis in this chapter, or this section, sorry, is going to have the general form mu1 minus mu2 equals the hypothesized value. Now in this course we're going to stick to that hypothesized value being 0. So what we're going to see is that for our null hypothesis we're always going to set up either mu1 minus mu2 equals 0, or if you rearrange that equation just a little bit, the null hypothesis is that mu1 equals mu2. So basically the null hypothesis is there is no difference between the means. So that leads us to our options for an alternative hypothesis. There are 3. Some of you who've been paying close attention when we talked about proportions are already going to be able to predict what these are. We have 3 possible options. They are mu1 is greater than mu2, mu1 is less than mu2, or mu1 is not equal to mu2. That last one is going to be the only two-tailed test. The first two are directional, so those are going to be one-tailed tests. And obviously, as we've been doing, we need to check the random, normal, and independent conditions before we proceed with our calculations. But I'm pretty sure you guys know how to do those, and we'll actually get to look at those a little later. So to actually do a test, we're going to standardize x bar 1 minus x bar 2, and that's going to give us a two-sample t-statistic. Now, I want to actually break this slide down just a little bit so you guys can see what's coming from where. So this up here is our general test statistic formula. We have statistic minus parameter. So remember, the statistic is going to be this thing from the sample, and the parameter is going to be the thing we are theorizing about the population. And then on the bottom we have the standard deviation of the statistic. So usually we see this called the standard error. Okay, now we've talked about all these things before. We have formulas for them. First thing I'm going to cover is the statistic. So in the case of a two-sample statistic, that's going to be x bar 1 minus x bar 2. So basically, if you have two groups with different heights, you're going to actually look at the samples, see the difference between the heights. Now this parameter difference over here, mu1 minus mu2, that's going to be 0, right? Because we assume that there is no difference between the two groups, and that's where we kind of do our starting point in this course. On the bottom is this standard error formula, right? And I want you guys to remember that this is the same as the standard deviation of the statistic formula, but it's got these S's instead of the sigmas. Okay, so this is going to be calculated from the two samples. We've got S1 squared over N1 plus S2 squared over N2. And that's going to be different than the sigmas, which come from the population parameters. To find a p-value here, we're going to take our t-score, we're going to put it into the calculator using TCDF and the degrees of freedom usually given by technology. Today, in addition to showing you guys how to do this kind of the old school way, I'm also going to show you how to do this on the Inspire calculator, which I actually should quickly which I don't know that I have installed here. But for now, we'll just show the old way of doing things, and I'll also look for a video that shows you how to do the 2-sample t-test on the calculator so that you're kind of familiar with that. So if the following conditions are met, we can proceed with a 2-sample t-test for the difference between two means. And by the way, if you're not already in the habit of naming the test, get in that habit. It can actually avoid you having to use the formula if you name the test, which can be another way to earn some points. So we need to check the conditions. First of all, random. The data need to come from either random samples of size N1 and N2, or by two groups of size N1 and N2 in a randomized experiment. So a lot of you guys are used to looking for SRS in the text of a problem. That's awesome. Remember also that it can come from a stratified random sample or a cluster sample, as long as it's selected randomly. The other thing is that this chapter, more and more, we're going to see randomized experiments instead of observational studies. So you want to see if it is an experiment that the groups were randomly assigned, or participants were randomly assigned to groups, rather than seeing like random sampled from a population. For the normal condition, this is a t-test, so what we're basically looking for is both groups to be large, right? So N1 greater than 30, N2 greater than 30. Unfortunately, I'm almost immediately going to show you a case where we are flexible on this. And in that case, you would just look at the data, a graph of like a box plot or a dot plot of the data to see whether it was relatively normal, and then you'd probably proceed anyway. For independence, you guys hopefully know by now that we are looking for both the groups to be independent, and we are looking for each group to be at or less than 10% of the population. That's our 10% condition. Just to kind of summarize here, we've got our big formula. This is our t-stat formula, and you can see down here we've got our 3 possible hypotheses. So remember, this is going to be our greater than case, this is going to be our less than case, and over here we do have our two-tailed case, which means we're just going to be doubling that p-value. Okay, so this kind of brings it all together. By the way, if you don't have technology on hand, which is usually how the degrees of freedom are going to be calculated, you would use the smaller one of N1 minus 1 and N2 minus 1. So if we imagine 2 samples, one of 11, one of 10, we're going to use the smaller sample, which is 10, and use then 9 degrees of freedom since we subtract 1. Okay, so let's look at our example for the day, and this is calcium and blood pressure. So our big question today is, does increasing the amount of calcium in our diet reduce blood pressure? And I just want to highlight that one word, reduce, because that's going to tell us that we're dealing with a one-tailed test. So examination of a large sample of people revealed a relationship between calcium intake and blood pressure. This relationship was strongest for black men. So they actually did follow-up, because obviously you guys know that observational studies cannot establish causation. So researchers therefore designed a randomized, that's good, comparative experiment. So we're dealing with an experiment here. Our subjects are these 21 healthy black men who volunteered to take part in the experiment. That's good. They are randomly assigned, that's good, to 2 groups. We have 10, it's going to be probably our N1. We have 10 of the men receiving a calcium supplement for 12 weeks, while the control group, interesting, of 11 men, so this is going to be our N2, received a placebo, okay, so they are the control group, that looked identical. The experiment was double-blind, which means neither the people administering the treatment nor the people taking the treatment know what they're getting. And the response variable is the decrease in systolic blood pressure for a subject after 12 weeks in millimeters of mercury. And this is a weird part of this problem. I'm going to highlight it as well. An increase appears as a negative response. Okay, so an increase appears as a negative response, meaning that if that number If that number goes down, then we are seeing an increase here. So group 1 with the calcium, we are seeing, let's see, we're seeing 7, -4, 18, 17, -3, -5, 1, 10, 11, -2. So right now what I want you guys to do is actually pause and put this data into your calculator in one column in either the Inspire or the 84. And then you want to go and do the same thing for group 2. And if you're on the Inspire, meaning you can label those columns, you should name one calcium and name the other placebo, and that'll make it really easy to go through all the steps that you want to do here. So the first step would be actually to graph the data. Now I have it graphed here. You can graph it pretty quickly on the Inspire if you go to the data and statistics page and then put either calcium or placebo on there, and then I think you can just actually, if you go to the menu, you can add an X variable and just add the other one. But if you don't have a calculator on hand, you can simply look at these dot plots. So the one that is pretty good is the placebo. I think you guys would all agree with me. That's relatively normal. And then we look at the calcium, and this one just is not as good. But what we're seeing here is really not a lot of skew, which is good. This is relatively symmetrical, and we don't really have any major outliers. I already know that one of you is going to say that these guys are outliers, but because there's 2 of them, I think we're okay. So we're going to say there are no outliers. So that means it's actually okay to proceed with these T procedures, even though our sample sizes, as you guys can see, are well below 30. Okay, so we're going to go ahead and actually move into the condition checks now. I don't know if I've covered some of this up, but here are our main hypotheses. So basically our null hypothesis is that mu1 minus mu2 equals 0, and mu1 minus mu2 is greater than 0. And what we're looking at here is mu1 being the true mean decrease in systolic blood pressure for healthy black men like the ones in the study who take a calcium supplement, and mu2 is the true mean decrease in systolic blood pressure for healthy black men like the ones in the study who take a placebo, and we are going to use an alpha level of 0.05. Okay. For the purpose of this study, mu1 minus mu2 is going to be greater than 0. That's our alternative hypothesis. There's a lot of negatives going on in the language of this study. I encourage you to look carefully through those, and if you do have questions about why that is greater than, please feel free to send me an email and we can chat about that. But in the last class, we were able to determine that, yeah, that was correct. Okay, so if the conditions are met, we're going to do a 2-sample t-test for mu1 minus mu2. So first of all, yeah, we have randomness because the 21 subjects were randomly assigned to the 2 treatments. Secondly, with such small sample sizes, we need to examine the data. We actually did that on the last page, but you're going to see this again now. And what you see are that, the box plots are okay. The normal probability plots are okay. There's nothing that tells us that these populations or these samples are distinctly non-normal. So we're going to go ahead and do our procedure. And independence, these 2 men are probably independent because we have randomly assigned them. And individual observations in each group should also be independent. If you know one subject's change in blood pressure, that shouldn't give you information about another subject's response. Also, the ever-important 10% condition, we can assume that there's more than 210 healthy black men in the country, so we are well below the 10% mark for the population. Since those conditions are satisfied, we can actually perform a 2-sample t-test for the difference mu1 minus mu2. And this is what that math is going to look like. So again, we are rolling back out this t formula, okay? So we got the x bar 1 minus x bar 2 minus mu1 minus mu2. Remember that this part is going to be 0. And then on the bottom we have to plug in sample standard deviation 1, sample standard deviation 2, sample size 1, sample size 2. So here we have a t distribution. This has 9 degrees of freedom. Remember, we're using the smaller of the two sample sizes. And we have the p-value is whatever this area is down here under the curve. Now with a t-score of 1.604, and we'll talk about exactly how you can get that, well, you can see it happening up here. With that t-score, I'm going to guess that this is going to be a non-significant finding. And I actually would be right. So with a t-score of 1.604, if we use table A, or one of the tables, that's going to fall between 0.1 and 0.05, meaning we are not under that 0.05 mark. So if we use that, we can use table B to show that the p-value is between 0.05 and 0.1, which means because the p-value is greater than alpha of 0.05, we fail to reject H0. So the experiment provides some evidence that calcium reduces blood pressure, but the evidence is not convincing enough to say that it reduces blood pressure more than a placebo. Okay, so that difference, we cannot say that that difference is greater than 0. And that's actually where we are going to stop for today. So we went over the formula for the t statistic. We went through the conditions. We actually performed the test, and we came up with a non-significant result. So that's basically what we are doing in this section. And as a reminder, this is our last section in this chapter, and then we're passing on to review and the unit test. The other thing I'm going to post today is a video, and it's actually going to show you how to use the calculator to do a 2-sample t-test. Now, the way the AP works, and this has been confirmed to me a couple times, is as long as you state your formula or the name of the test, meaning 2-sample t-test, I'm going to circle that up here. As long as you state that you're doing that, you can run the test in the calculator and write down the degrees of freedom, the t-score, and the p-value. And that should actually be enough information for a grader. And when you watch the video, you're going to see that actually the calculator will print all that out for you if you give it the data sets, and you won't really have to do a whole lot of other work. So I'm going to stop there for today. I'm going to post that other video with the calculator, and hopefully this should prepare you to do any 2-sample t-tests that you need to do.